Okay, let's continue our lecture on the recommender system. So this is the third lecture. So like today's lecture, we'll talk about the coding part. So I'm going to demonstrate some of the examples with highly popular data set, movie lens data set. We are only using the smallest set of the movie lens one, which is 100K data set. In the Homo project, you're going to do a little bit bigger data set. But of course, you can and try a much bigger data set for that movie lens data set, which is so very popular, a benchmark data set on the recommender systems. Okay, so all right, so let's see. So this data set has 100K movies with rating, so ratings by the user, which we have talked about this. So the rating is 1 to 5. The main idea, the data set has basically has 4 columns. One is the tab, and including the user, which is item, the rating, and the timestamp. So basically, we are going to using the user ID, item ID. Both are starting from 1 instead of 0, and we're rating from 1 to n. I didn't use any timestamp here, but you can use that in your Homo project if you want. Okay, so let's unzip the data. Let's just load the data. So you can see this is actually the user ID, this is the movie ID, this is the rating. Okay, so in total we have a 100K so ratings from various different users to various different items. So you can see only the data set that we have is how each user interact with each others. So this is basically the usually data set we have. We don't have that sparse matrix constructed. It's very common because sparse matrix is sparse, so we don't actually store that sparse matrix. We only store the data that we have user and interact with each items. With that, information, what we do is we first construct a user item matrix. That means it's that sparse matrix, with each user being the row and item being a column, as I mentioned, right? So this is basically it's commonly used methods and the consensus. The value for each cell is just being simply the rating that user give for that item. So that's the matrix A we have been talking about. Okay, so and of course we need to and print out something to see like how sparse of this and the matrix, and we have some good idea on what kind of stuff that we are working with. Okay, so so first things we create this and rating matrix. I want to emphasize we need to subtract the user and ID by 1, since in Python the indices start from 0. So this is being the way right here. So if we just find out the number of unique user and a unique item, which is unique movie that we have, we actually only have 943 users and 1,682 items. So this is turns out a very small data set. And we only have a couple hundred and a couple thousand movie and the users. So this is a very tiny data set. In the home project, you are going to do a slightly bigger, but in practice, I'm actually aiming a much bigger so matrix and data sets. Okay, so we can also we need to see like how many elements are actually filled. So basically, it's the sparsities of the matrices. So we're trying to find out compute number of non-zero elements in that matrices. We calculate, so this is basically called sparsity. So this sparsity is actually about 6.3%. So that means with that rate and the rating matrix, only 6.3% of cell have a value. We just simply fill those empty ratings being zero, but we shouldn't assume these values are truly being zero. It just being says we have missing values. As by default, we just treat this as a zero. In fact, this is and these kind of sparsity is very common in recommender systems because people usually don't give the ratings for all the movie they purchase or all the items they purchase, and there's no way that they can watch all the movie they list in the library. Okay, so this is and that kind of like problem is very, very common. All right, so and the one thing that that you have something in your mind is, as a rule of thumb, usually the sparsity is very, very low, and usually below 1%. So this is, I mean, so 1% to 6% is okay, but if it is below that 1%, this data set may be too sparse to perform any sort of model. So 1% is the and the rule of thumb. Basically, anything below the 1%, you shouldn't use that. Right? So this is too sparse. Another tricky thing is, naturally it doesn't have testing data set, right? So we have training already. That's all. I mean, we're only giving that amount of data set, and doesn't. I mean, to be very obvious to split the training and testing in these cases. It's very important that we have some testing data set. Otherwise, we cannot evaluate performance. I mean, if we don't have testing data set, we don't know whether you are hitting the overfitting or not. So, so what we do here in the recommender systems, I mean, it won't work because all of the items the user need to be available when the model is first built. So what we do instead is, I mean, this is very important, is we mask a random samples of user items to validate and compare how well this recommender system did in predicting the ratings. So in this case, what we do is for each user, we find out they all have more than 10 ratings. So what we do is for each user, we will remove 10 of the items ratings and assign them to be a test set. So basically, I'm going to split this 100K interactions. So what we're going to do is we're going to separate the training and the testings. So basically, I'm going to remove 10 item ratings for each users and assign them to be a test data set. So this is how we are doing here. Just a second. Okay, so how we do it here is like that. So first we so this is piece of code is the thing that we are doing here. We're going to split the whole data set into training and testing data sets. As I said, remove the 10 readings from each user and assign them to the testing data set. So so that means I'm going to copy I'm a testing and training here, but the difference is for each user, I'm going to randomly select 10 items that has been rated. Then I'm going to assign the training part to be 0 and then testing part to be that portion. Right. So basically moving those ratings from trainings into testings, right? So they don't actually intersect at all. And you can check whether this training and testing set are truly disjoint, right? I mean, if it is like truly disjoint, that means if in testing it is non-zero, in training it has to be 0. So I mean, this is the key of the train testing split. All right, so so we have created this. So you can see this is my training. This is my testing, right? So this is pretty and a pretty large and a matrices. So the reason that here is this matrix is not big. It's it only has a couple hundred, a couple thousand rows and columns. You don't actually need to using sparsity matrix to specify that. And just like you can just and literally print it out. But in the, I mean, if you want to work much larger system, you probably have to using and sparsities to make sure you fully and take advantage of the sparsity here. Here I'm going to using the second approach that we have talked about in this course. So it's a matrix factorization model using ALS, which is the alternating least square methods to predict those empty entries in a matrix. All right. So it comes with 3 parameters. It's number of iterations that needed, number of factors, which is k, that we have talked about this, and some regularizations, which is the lambda. It's like basically Frobenius norm of the W and H matrices. Okay, so the key here is, so this is initialization. So this is my ALS step, right? So it's nothing but you just plug in what we already have. It's basically this matrix transpose times some, and in this matrix, this fixed matrix can be W transpose W or like H transpose of H, right? So it depends whether you are doing the iteration for W or depends whether the iteration for the H, right? It's almost all the same. It's just because of the whole thing, it's symmetric. You can do W or H simultaneously. All right, so I mean, if you do that, this is basically, this is universal ALS step for W or H. So this is things you don't need to actually do it twice, just do it once. That would be good. I mean, for the I mean for the prediction, this is pretty straightforward. This is like and a W and the dot of H transpose. So this is my W, which is user factor. Item factor is H, W dot H transpose. And then you actually, so we'll talk about this MSE later. So this is part is the main portion that we have. It's our fitting functions. So we initialize our user factor and item factor. Y is W, Y is H, right? So it's number of users times the K, numbers of items times the K. Both are random. So we are going to record the training for each iterations to see whether it's converging or not. Let me just make sure I run this. So this is an ALS step. So so basically the differences is we first apply the user factor. The second one is to apply the item factors. So this is W, this is H. So you can think about everything being like flipped, right? So you think about our A, which is our training matrix, is equal to W dot H transpose, right? So this is, but if we take the transpose on the both hand side, this becomes A transpose equal to H dot W transpose, right? So then everything just being the and flipped with a W and an H, right? So, and you can using exactly the same formula that we already have for the W, and it can be applied to the H. Right, so that's why for this way you can only need to write one ALS functions just by taking advantage of the symmetry of W and H in terms of this dot product that we can using this universal ALS step. So this is a little bit I'm slightly trickier just because we are going to use certain like linear algebra knowledge to help us to and reduce the complexity of the programmings. Then you do the prediction. So the MLE here is very important because you're going to use that in the project homework. So basically what you do is, say you already fill up all these training data set. So you like unravel. So basically it's you flat this matrix out. And this is the predicted one, which is which is my predictions. And then you just get those like non-zero portion of the training, because those are zeros that are missing data. We have no idea what is truth. What we can only calculate for the MSE is actually for those non-zeros. I mean, with the zeros, we don't know because it's missing. So we calculate the room and mean square error. So basically, it's our predictions subtract the trainings for those mask values, which is non-zeros, square them, sum them together, divided by the number of masks. So, and it's literally the that I think I should numpy here. Just make sure. So let's see. Is it right? Okay, let me see. I might be wrong here. To change this. Is it mask? Okay, so let's see. ALS. Oh, ALS not defined. Okay, I need to change this down. Okay. So let's initialize this. See what it's working here. So we initialize with 100 iterations. Ki set equal to 20. The regularization is 0.01. Okay, so that's good. So this actually we plot the learning curve. And it's basically it's MSE versus iteration. So I want to see how this MSE drops along with the number of iterations. And then this actually show you the training label right here. So this is training. And training loss, you can see it start, I mean, above 2.6, then true, it's dropped very quickly and it becomes flat. So that means it already converge, maybe in 20 or 30 iterations, right? So 100 iterations is overkill here. So you can see those like user factors, which is my W. You can see this should be about 900 by 20. So you can see the shape. Yeah, 943 by 20. But the key, I mean, interesting part is if you look those value here, those value are actually some value are negative. So because we are just using ALS doesn't preserve the non-negativity. So basically, it could be some like an inactive entries showing up. Okay, so then what we do is we can test on the testing data set. So basically, this is validation here. We have so this is basically my validation. So validation is I'm going to passing my testing data set and to make these predictions. Then I'm going to compute MSE with the test and the predict. Right, so this is very simple. So I make this prediction for my testing data set. Sorry, I make this my prediction that I'm going to compare those non-zero entries in the testings to ensure whether they haven't seen these data and how well they can predict. Right, so that's what we are doing here. So this is prediction here. we're actually getting 2.83, right? So which is okay, but can we do better? So one of the thing is we didn't specify any of my K's, right? So K is I think I said it 20 right here, but who knows, right? So I mean, so why and why 20? So what you can do is you can using cross validations to find out the best case that you should be getting here, right? So here I'm treating this testing data as our validation data set. We're going to be using this and the testing data set as a validation data set to do the grid search to find out the best K that we have. Say our K is ranging from 10 to 29, so this is basic around 20. I'm going to loop through all possible K, and each of that I'm only running 50 iterations with and vectors from 10 to 29. My regularization is remain to 0.01. Of course, you can change that regularization if you want it. Then I do the fittings. Then we do this and testings, right? So basically just and validate with the testing. The only difference is I change this number of factor, which is the K, to see how this changes. So you can see, you can run. It take a bit while. You can see this start to decreases, and it still decreases. Then they start to increases right here. Okay. Okay, they run it off. They finish running. You can plot them out. You can see they start to decreases, then start to increases. So this is actually a U curve, an U-shaped curve that we are interested in the cross validations. So you can see right here, the lowest point that you can get is about K equal to 17. So this is basic indicate the best K, best the number of factor, if 17. Okay, so this is basically very good. But you can see this actually, I mean, doesn't change too much. Highest you can get is 2.855. The lowest is 2.83. It's only differ by 0.025. So it's tiny. So that means if you change this and the number of factors, so the variation is not very big. Okay, so it's all equally very good. But if you have to choose one, the best one is happen to be the 17. So this is very premature analysis that we have done, and of course, and in the homework project, you can do much more complicated. So this is just a say a starting point of everything, but in the homework you are actually project actually you need to do much more complicated things. All right, so this is for this notebook and the code demonstrations. So this is all about explicit feedback. Next, we're going to talk about implicit feedback. Okay, so implicit feedback is also a very important part. So basically, in explicit feedback, we assume the user will give some ratings for each item they have interacted with. But this is a very restricted assumption. And for example, if you have watched a movie, if you purchase an item, it doesn't necessarily you will rate for every item or movie that you have interacted with. So in general, a more realistic version is you want to learn from the implicit feedback that the user gives just by interacting with the system. So this is some like positive information that I already have. you can view this fact that they watched the movie I, but didn't watch the movie J as implicit signals that they prefer I to J, because you give a bunch of recommendations. Instead you picked I versus J, so this already gives you some preferences that you like to watch I instead of J's. Even when we do have some explicit feedback, it's sometimes a good idea to incorporate this implicit data into the models. For example, in the home project, you're going to work with some like listening to the songs. When the user listen to the music on streaming services, they might, as I said, they might really rate a song, but more often they skip the songs. Only like say you only listen like 50%, then you through that you don't like it, then you skip that. But if you really like a song, it will come back to listen again, again, again. So this is, although you don't give any like, feedbacks, but this already give you some preferences, right? So because if the song then you can skip only half through, that means you probably don't like it. But if you come back to listen again, 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 that means you like it a lot. So in fact, you can using this information that without even have the explicit feedback, you can infer the and users' taste profile, their listens and repeat listens, all these kind of skips and fractional tracks, maybe a good valuable signals than just explicit ratings, because explicit rating is very sparse, it's very rare, but those data actually is very rich. Okay, so we can do a lot of interesting stuff, right? So to work on this kind of problem, it's turns out not very easy, because a possible method, as a method is you can treat all the entries being zero and minimize the loss for all entries. If we want to do matrix factorization, then we do similar things like W and the dot H, right? But the issue is they are all 0 and 1s, because we only track what and whether they have interacted with that or not, right? So if they have some interactions, this will be 1. If they don't interact, it will be 0. But the consequences, most of elements are actually 0, so it will tend to fit the zeros instead of 1s. So by the end of the day, they just trying to minimize all the entries as much as possible, because most entries is 0. So if we're trying to do a naive matrix factorization on this kind of implicit problems, it would just give me basically as 0 as possible, right? Just give me a 0, because since most entries, maybe 98 or 95% of entry is 0, you just predict everything to be 0. So this is a very typical imbalance problems, right? And also we can using exactly the same method that we had in the explicit feedback, that a user has interacted at all with, if the user has interacted with an item, then you just set PUI equal to 1. However, when PUI equal to 0, we assume it should be associated with the lower confidence, as there are many reasons beyond dislike the item or why this user has not interacted with it. And for example, unaware of this existence. So basically, if the and the user has interacted with I, that sort of okay, they have some interactions. But if they haven't interacted that, there are 2 possible reasons. One possible reason is I have seen this recommendation, I saw it, but I still don't want to do it because I don't like that movie or I don't like that song. There's another possible way is I'm completely unaware of, which is very, very common because there are so many millions of songs and millions of movies. But why should I watch that or listen to that specific songs or movies? Right? So there's no reason. And that means I'm completely unaware of the existence of the situations. So this is also very common. So I'm going to talk about maybe one or two methods that we have that we'll use, and you can use that in your homeworks. All right, so let's do some math here. So basically, in this cases, I'm going to come up with the new objective functions. So for this implicit problems. Okay, so this is very different. So the first things is this, I mean, this loss is different. So like objective function. So this objective function, I'm going to call, I'm still LWH. But now this time, this is actually equal to, I'm trying to do the following thing. Is minimization. Again, my W and H, right? So same thing. I'm going to do a summation of U and I in omega, which is the same because that's the only data that we have. Here, I'm going to have a weight of CUI. Then my PUI subtract WU HI transpose. This is the same. So the difference is I have some CUI as a confidence. Subtract plus the Frobenius norm of this, right? So this is basically the same thing. So this is PUI is the following. Is one, if they have any interactions, right? If zero otherwise. So CUI is the confidence in observing PUI. So I mean, it's very important that we need to separate the observation of AUI into two very distinct and the representations, and the PUI and the CUI. So this is basically has a two level, and we need to split the PUI and the CUI in different scenarios. So I mean, rule of thumb of idea is when AUI is equal to 0 and the PUI is equal to 0. Right. So I mean that means it's like, and actually and for this it has a two possibility. One is negative, one is unobserved. So that means I didn't actually saw these things. Okay, so that means I should have a lower weight of CUI because I'm not confident whether this is 0, that means a negative, or that is unobserved. Okay. So I mean, this is the first part. The second part is when AUI is actually equal to 1, the bigger than 0, so that means they have certain interactions. Then PUI is actually has to be 1. That is always positive. But in this cases, we should have a higher weight because we note they have some interactions. Right. So because, for example, they have watched, that movies maybe halfway or longer, so that I have a higher confidence to say it is relatively positive. So, and also the higher of AUI, the higher weight of CUI. Right, so because if the weight is higher, that means I have intact more, and of course I have higher confidence. That indicate I have a higher confidence level. So there are multiple methods to have a CUI. So one possible choice is the first is CUI is equal to A plus alpha AUI. Right, so this is something that has the fact that the larger of AUI, the higher weight of CUI. Okay, and also if it is 0, then this is 1. Okay, or the second choice is my CUI is equal to 1 plus alpha logarithm of 1 plus AUI divided by epsilon. Okay, so this is something also possible. So basically, this actually alpha here controls the rate of the increase. In the homework or project, I will tell you what is alpha we should be choosing here. Okay, so this is something. So a higher, so the higher of CUI, so that means this actually will contribute more on the weight. Then my WU HI transpose should be close to UI because I have a high confidence these two should match, right? So, and that means these two should close to be that. If it is lower CUI, they may not be very close to each other. So it's okay. And that means the weight is lower. So, but if they are higher, these two should be close, such that this term will not contribute too much to the total loss. All right, so how can we solve that problem, right? So it's still the alternating least square, but it's a different way. Okay, so I'm using this method again. Okay, so again, we have M users and items and the K number of factors, right? Or hidden dimensions, same thing. Okay, so it's basically same. Say we treat HI being constant and solve the loss function with respect to WUI. So the idea is the same, is treat HI is the constant and solve loss function with respect to WU. Okay. So and of course, so the better way that we can do is we rewrite this loss function in matrix form. Right. So I mean, if we rewrite everything in terms of matrix form, for a given U, so this is, I want to remind you, my UI is CUI PUI minus WIHI transpose square. So there are two. Here we assume HI is fixed, right? What actually is varying is WE. So this is equal to summation of U of CU PU minus WU of H transpose, right? So here we are not using the square, just taking a norm because this becomes a vectors. Square of vectors. All right, so we sum them together and we split it up. But okay, so like splitting this up is not that straightforward. So basically, and you need to think about this whole thing is actually a vector. So basically, this is x, and I mean, if you think about, I mean, x as being a row, this is XX transpose. So this is basically written in the following way. It's I mean, if you do this, this becomes that PU. This is C of U. So I'm going to tell you what is C of U momentarily. I mean, this is kind of the weight. PU transpose subtract 2 W U H transpose C of U P of U transpose plus W of U H transpose C of U H W U transpose. And so I have 3 terms. So I mean, this is basically coming from the expansion of this. But what is C of U? Where C of U here is actually a diagonal matrix with diagonal of CU. So it's a diagonal of CU. Okay. So this PU right here is the U row of P. Basically, it's the row vector has all the preference of the users. Right? So this is that. And we know UI, the H is a constant right now. So we can set everything in term, into a constant. And also CU is also a constant because this is already given. The only thing that is varying is my like WU here, right? So here is what I'm going to do. I'm going to set everything to, everything is constant, being a constant, H transpose C of U and H, and the B is H transpose of C of U. Okay, so then the whole equation becomes the following. So right here, so this thing is being the same. C of U, P of U transpose, subtract 2WU, B, P of U transpose, plus WU, A, WU transpose. Okay, so this is actually a quadratic problem, and you can solve that by taking the derivative with respect to that. So, and I want to remind you, I mean, the full loss actually has the penalty terms involved that. So, and you make sure that you don't forget that. So partial, I think I'm using L here, right? So, yeah, L here. Partial L, partial WU, right? So we have this term here. So this is 2b minus 2b pu transpose plus 2a wu. Oh, sorry, I don't have a transpose here. I'm just being bu here. And also is that right? Yeah. BHU transpose. Just a second. I think I might miss something. Yeah, I think this is there's a mistake here. This should be transpose I'm missing here. Right here. So this A is this P U transpose. For the partial derivative, this is missing a transpose here. This is also a missed transpose. Okay, so yeah, there's a missing a transpose here. I'm going to correct that in the notes. By the end of the day, it gets you W U transpose. Okay, so this is like that, should be like this, plus 2 lambda of WU. And we know we're going to set this to be 0. And this is basic to say A plus lambda identity times WU equal to B PU transpose. Okay, so as a result, this W star is actually has analytical solution is A plus the I inverse B PU transpose. Okay, so this is and obviously a very important part. So you can do the similar things, but so basically this PU transpose is a column. So oh, that's why. Wait, it's a row or column here? It's a row. Okay, it's a row. The WU is also a row. Okay, but you need to take the column. So just a second. Yes, I think that's right. So I'm going to leave as it is. Similar things, you can do very similar things to take partial derivative with respect to HI. It's very similar, the whole idea. So if we treat WU as constant and solve for HI. Then your HI is actually comes D plus lambda I inverse E and the H transpose, taking the ith row. So then this D right here, we can do it similarly. W transpose CI W. And the E is W transpose CI. Okay, so I mean, for each iteration, it will be quite expensive to calculate this iteration because and because of the CI here and the CU here. So CI CU is very, and it need to be calculated for each I and each U, and this will be very expensive. So the some trick that we can use is we can take this W, say the and just the WT CIW. I mean, this is very expensive to be calculated because for each CI, that you have to calculate for that. So what we do is we're going to rewrite the whole things in a different ways. And the same as H transpose CU H. So this two, and for example, this one will becomes H transpose H plus H transpose CU minus identity of H. This is W transpose W plus W transpose CI minus I W. Okay, so so the key is these two are actually independent. It's independent of each user and each item can be computed independent, and we can pre-compute everything. These two things, okay, so these two things only has, and for example, only has NU non-zero element. So that means NU is the number of items. This is number of non-zeros of R RUI. So basically we know this is sparse. Most of the part is just being zero. We only need to take operations very limited times. So that means this part we can take advantage of sparsity. So that means only a very limited number of element is being used. And these two operations can be take advantage of using these sparsities. And you're going to implement in the homework project. Okay. And also the key is these two things actually can be computed separately. So you can just compute W transpose and HA transpose. Just store them. Then the rest of things can be computed with the sparse matrix and ideas. All right, so this is very important, and you guys can and are going to implement that in the homework project. In the last part, I will talk a little bit on this matrix factorization with the parallel and Wise laws. So this is also another method that people can use, and you can use the stochastic gradient descent. So idea is basically the same. is using pairwise comparison to design the loss functions. So the idea is, if UAI is 1 and AUI is 1 and AUJ is equal to 0, that means the user U is prefer I over J. So this is basically has some preferences. So in these cases, you can think about WU and multiply and a dot HI transpose should be larger than WU dot HJ transpose. So what you can do here is you can choose this pairwise loss that to include this effect, right? So you want to have WU dot HI transposes minus HJ transposes. In the cases that for the same UI equal to 1 and the UJ equal to 0. So you want to find out a pair of index of IJ such that you have that kind of phenomenon, right? So that means you want this whole thing to be as small as possible, right? So this is the key. So that becomes an optimization problem. Actually, you can think everything as a classification loss. You want this to be as positive as, so as much. So what you can do here is you can using these bunch of different loss functions. For example, you can use hinge loss, which is being used in the and SVM soft and SVM, or the logistic loss, which is being used and a lot in the logistic regressions and stuff. So so with that, actually, you can do this kind of stochastic gradient descent methods, all right? For each iteration UIJ, you can sample a user U, and you can have a positive item I, and find out a negative item, which is unobserved, AUJ equal to 0. Then you can calculate for this sample loss function just for one observation data of WU, HI, and HJ. So this is basically your loss functions. Then you can update WU, HI, and HJ by stochastic gradient descent. Take a gradient with that. Just take a tiny step. That would be good. So here, I think I should have a ADA here to ensure this is I have a learning rate. Otherwise, this won't work. Okay, with that, we can actually take advantage of stochastic gradient descent to quickly converge to everything. And otherwise, we need to do a lot of difficult matrix inverse if we're trying to using gradient descent. But if we're using stochastic gradient descent, and this whole thing can be done very quickly, and everything can be estimated entry-wise. All right, so this is a method that I just briefly mentioned. In fact, you don't need to program that. For this and weighted matrix factorization with the method of alternating least square, you actually need to do that for the homework project if you need it. This is actually being done right here for the task 2 right here. And also right here, I specify my alpha explicitly. My alpha right here is actually my sparsity ratio. I also give my f equal to 3, which is the k. In my notes definitions, and the lambda being 0.01, right? So this is the whole thing, and you're going to implement this the whole algorithm we have mentioned by taking advantage of the sparsities, which is extremely important fact that you need to use. So if you don't use that, your code will take really long time to run, and you probably won't finish that. So you have to make sure you implement everything into consideration of the sparsities. I also provide some hint. That means if you want to work with that large data set, you should start with a small data set. So after one iterations, this loss function will be between was 1,400 and 1,600. After 100 iterations, a top 5 favorite artist for user 1 is, include 30 and 95. So this gives you some idea whether you are getting the result correctly, right? If you don't get the result correctly, this and this hint 1 will give you some idea, right? So this is always try to start with a small data set, then before you work on the large data set. Hint 2, of course, you need to use the trick that I already mentioned to speed up your implementations. Otherwise, it will take forever to run. All right, so that's everything I want to talk about, and I found for that specific problem, it will take a while, but it's definitely worth it. All right.